Hello everyone, my name is Andrei, and in today's tutorial I want to show you some techniques of working with data inside Substance Designer. We have four examples here. The first example is uh, scattering a bunch of points into this space. Their position is random. You can change some of their properties, like for example the scale and uh, their luminosity based on some input map. Then we will use the pixel processor node in such a way to write a list of values in order to generate this kind of spiral. Then the next example, we will create a spiral like this where we will have one larger spiral, one smaller spiral, and then we will draw lines that will connect the points. And you also have this option of changing what points are connected to what points. Okay, and in the last example, we will draw a list of 16 points, and then we will generate another 16 points radiating, or we will generate for every of those 16 points we will generate a ring of other 16 points. And the main focus of these tutorials is working with data in Substance Designer. If you are familiar with software like Grasshopper and Houdini, you probably know that those are similar. These lists in Substance Designer, lists of data in Substance Designer might be similar to the lists of data that you have in Grasshopper and Houdini. And these lists of data contains like attributes like position and velocity and scale and color and things of this nature. Okay, so let's get it started. We will use pixel processor and fx map. With the pixel processor and some nodes we will generate the data, and with the fx map node we're going to read the data and draw something using the fx map node. Okay, so I want to generate a list of random positions. In order to do that, I will use the white noise node, white noise fast. I will resize it to be 256 by 1, so it's a long row of 256 values. I will duplicate this changed seed to have a different set of random values. I will use another pixel processor node to bring these two lists together into a list of vectors. So those black and white values are scalars and colors are vectors. We're going to use this variable to be able to create space coordinates and then read in or bring in the values. So right now our pixel processor looks like this, so it's reading the first texture and then actually copies, or yes, it copies the same row over and over again. We don't want this, we want to resize this texture to be of the same size, and also we want it to remain color. When we want to change the format from 16 bits to 32 bits, go inside, sample the other incoming image, compose a vector, and set this as an output. Always remember to look here. So it's here, this text is going to tell you inside the pixel processor what is the type of value that it's expected as an output. So float 1 or float 4. So if we can right click on things that are float 1 and set them as an output node. This one, for example, is a float 2. We can right click, but we can't set this as an output because this is not either a float 1 or a float 4. Okay, so we can output this. So right now every single pixel in this texture or in this list represents a position into this space, and we're going to use the fx map node to read every single pixel one by one, and it's going to read the first pixel and place a position into this space at this location. Then it's going to go and read the next position, and it's going to draw a circle in the 2D space at this position, and so on and so forth 256 times. Good. fx map, make it grayscale, plug the positions into the image input 0, go inside, double click on the fx map node to see the result. Right now nothing happens. Go and change the pattern to disk, change the size of the disk, not like this but here. Okay, good. Now we're going to iterate, use the iterate node, plug the quadrant node to the right side of the iterate node, right click on the iterate node, set it as a root, set the number of iterations to 256, go into the quadrant node, into this channel where it says pattern offset, empty function, get the number. We're going to get float, then from this drop down list choose $number. We're going to divide this by 256, then make this a vector. For the y component we're going to input 0, then sample, and then extract the float. So again, we want to output this out, and the type that this channel is expecting is float2. And what we're doing right now is the $number variable generates a list of values from 0 to 255. If we divide this by 256, we're roughly getting something from 0 to 1, and it's what is happening. The fx map node, it's actually going into this texture, and it's going to one by one move and read every single pixel here. Okay, and then I want to actually visualize before before outputting the result. I want to visualize this and disable temporarily the tiling because I want to show you something. And now as we output this, we get the scattered random points into the space. And the reason I deactivated the tiling is because I wanted you to show you that we're getting only this corner being populated by points, and the reason for that is the fx map node considers 0, 0 coordinate to be here in the center. And in order to fix this, we're going to go here into the quadrant node, and we're going to use this branch offset to fix this. So 0 minus 0.5 minus 0.5 and minus 0.5. Okay, so now we're good. Excellent. And the second thing that I want to achieve is I want to change the size of these points based on a gradient. Okay, so I'm going to choose a radial gradient, this one, and I will temporarily plug this here to explain what is going to happen. I want just to decrease its luminosity a little bit. Okay, like so. So you are familiar with how the tile sampler node works. You will plug in a gradient, and this gradient is going to control the size of your pattern. So whenever we will have a black value like this here, this dot here is going to read the black value from this map, and it's going to be decreased to 0. Its size is going to be 0, and everything, every point here that it's inside this gradient is going to go from small to large as the values of these gradients are higher and higher. So this is what is going to happen, but I want to show you how to do it in an interesting way. And for this I will create an fx map, another pixel processor node, which is going to be again the size of our list of values. It's going to be a color node. I'm going to make it 32 bits. And what I will do is I will use this texture, these coordinates, to look into this space and extract the values of this gradient that correspond to these positions. Okay, so this is a very interesting technique. You are looking with this set of values into this map and extract the relevant values for each position in this list. Okay, so plug this in, and notice this map is 1024 by 1024. This texture here is 256 by 1. Okay, going to get float to position in order to read our list of positions. Then I want to only extract the x and y, and then I want to sample with these values. I want to sample our circular gradient. Great. So you can see you get a bunch of scattered black and white values, and those corresponds to the radius or to the luminosity of the gradient at each of those random positions into this space. And we're going to feed this list of radius in to our fx map node. I want you to be aware that the fx map node has the size of the pattern controlled by two parameters, width and height. So for this reason we will output a vector float to that contains the two values for width and height. And also I want to make you aware that high values like bright pixel like this is going to draw like large patterns. So a bright pixel like 1 is going to draw a circle that is large as the entire image. So in order to avoid cluttering the image with too many large circles, we want to multiply this by small value like 0.05. Okay, then make this into a float too, so the width and the height are the same, and this will cause our circles to remain proportional and to be circles and not ellipses. And then we need to pay attention to the fact that we need to output a float for. Okay, so great. So I think you can barely see, but we still have some pixels here that are colored. Okay, good. So now this is our list of sizes. We want to plug this into our fx map, go inside the fx map node and go into the pattern size, empty function. Everything is right now it's white because all the circles are very large and they overlap each other, but we're going to use the same technique in order to read every single pixel in our list of sizes and then output that. Okay, so get float, we're going to take the dollar number, divide it by 256, make it a vector float 2, only read the first row in our texture, then sample it, then extract the x and y coordinates, and then we're going to sample the image that contains sizes and then set this as an output. Actually, don't want to do this. This is what I need to do. I need to, at this point I need to, so let me explain again. So I created, this is the list of coordinates that allows the FX map node to read pixel by pixel our list of sizes, and then I need to sample that. So sample color image input 1, because image input 1 is the one that has the sizes, and then we'll pay attention to the output here. So output is float 2, so I need to extract the x and y component. X is the width, y is the height, and then set this as an output. Okay, great. So you can see that our list of sizes here correctly reflects what is happening in this map. Okay, and I want to make an interesting effect. I will use a pixel processor node to modify this gradient in an interesting way. Go to bring the image inside this pixel processor like so, multiply this by high value, like maybe 10. Then we're going to pass this gradient to a sine function, set this as an output, so you can see that the effect of this is creating a set of concentric rings, and these parameters control how many rings do we have. The sine function outputs values from 1 to -1. I want to change that to the range of 0 from -1 and 1 to 0, 1, like so. And there is another parameter that we can use, and this is called the phase or the offset of the sine wave. So we're going to add a value like maybe 10. And if we play with this value, we're getting this effect, which is interesting. Great. So now instead of plugging this in, we're going to plug this inside the FX map node for the radius. We need to make this grayscale and see the result. Okay, so we have something like this, and if we play again with this value, we're getting this effect, which I think it's interesting. Now, the last thing that we want to do is we want to create a list of luminosities for every single point here. Okay, so we will create another list of luminosity, and in order to do that, we're going to make it based on this same image here, but you can change this with whatever you want. I will only duplicate this node to create the list of luminosities, go inside, delete everything after here, and just output this. So this is containing our list of luminosities. Make this grayscale, plug this inside the FX map node, and go into the quadrant node, under luminosity, repeat the process again, get the number, divided by the 56, make it a vector that reads pixel by pixel from in the x direction, but then it only goes one row, so reads only the first row, and then sample the luminosity which is contained in the image input 2, and set this as an output, and you can see everything changed. And I also want to make this maximum, so the quadrant node, it's the blending mode, it's maximum for it. Great. So going back here and playing with this value, you can see how size and luminosity changes based on our map. So we can use like a Perlin noise, not the 3D one. And this is only going to be for the luminosity. Okay, something like this. And then, yeah, so our disks are right now picking luminosity values from the Perlin noise. Great, this is the first example. In the second example, we will create a spiral like this. And initially we're going to create a circle, and then we will modify it such that it becomes a spiral. And we're going to again generate the data with the pixel processor, and then we will read and draw it with the FX map. Good. So pixel processor. Again, resize it into a list of 256 by 1, change the output format to 32 bits. And the reason for using 32 bits is because the other depth of the node outputs values from 0 to 1, but changing this depth into 32 bits is going to allow us to output values from or negative values and larger than 1 positive values. Okay, I'm going inside the pixel processor node, and I want to create a set of 256 positions, and I want these positions to be around the circle. And I want to introduce you to the fact that you can specify positions into this space by specifying the x coordinate and the y coordinate of a point, but you can also specify a position into this space by specifying a length and an angle. So we're going to do this length angle thing in order to place points around the circle. And the node that will allow us to do this is the Cartesian node. The Cartesian node, as you can see, has as input a length and an angle, and outputs a vector or a 2D position. Good. So we need to create a list of increasing angles, because we will start from a position around the circle, and by increasing the angle we will place dots at increasing angle along the circle. Good. So how to do that? We're going to get the position, we're going to extract the x coordinates such that we're getting a list of increasing values. The Cartesian node expects or wants values or expects values for the angle in radians, which are from 0 to 2 pi, and our current set of values right now is from 0 to 1, and we need to multiply this by 2 pi and plug this in here. And then for the length we're just going to use a constant value so far, like 0.2 as the radius of our circle. Great. So this list is going to contain 256 points around a circle. We need to output this, so for that we need to output a vector float 4, and this is our list of points around the circle, and we need to read it and draw it. So for this I will make another fx map node from scratch just to repeat the process, and I think you'll get used to it. So fx map node, make it grayscale, plug in the data into image input 0, go inside, change the blending to max, make the pattern a disk, change the size. Okay, great. Then use the iterate node, plug the quadrant node into the right side of the iterate, set the iterate as root, change the number of iteration to 256, go inside the pattern offset, get the dollar number, divide it by 256. So this is how we're creating a set of vectors that are going to go pixel by pixel into our list of values and read them, and then place circles at those positions. So like this, and then just sample the list of positions and then output the x and y, because we defined these positions by an x and a y coordinate, and then set this as an output. So you can see we're getting a circle, and this is the data, and this is what it's drawing the data. Going back here, we need to change this value. This is a radius and it's constant, so that's why we're getting a circle. But for example, if we were to replace this by something that's changing, then we're going different radius, and depending on how we set this, we can create like a spiral thing. So to make this interesting, I'm going to use a curve node, and it's important that the gradient is from left to right. It doesn't matter that this texture is larger. The fx map, the pixel processor node, which has one row, is going to read one row. I think it's either in the middle or at the top. So plugging this in here, and then just read the image, going into the fx map node to see the result, and if we replace this with this, we're getting a spiral. Okay, something like this. So the reason we're getting this result is because tiling is activated, that's why. And then the radius is too large, so we can multiply this by a number, and this will control how fast our radius is growing, something like this. And I want to do another thing. It would be cool if we would have a possibility to have this spiral winding multiple times around itself. And in order to do that, we need to multiply this by something like a larger number. Great, I'm happy with that. And what I want to show you is that right now you can change the radius with this curve node and get various results. Great, something like this is interesting. Now the third example. In the third example, we created two spirals with two set of points. One is larger, the other one is smaller, and we add them together. And the final step is to create lines that connect both points from both spirals. Good. So in order to do that, I will just duplicate this here. So our first spiral, I want to just go back and delete this and make it like a regular spiral. Then I will duplicate this and just make the second spiral a little bit, decrease its radius a little bit. And the reason for working with data, I want to say, to take the advantage or the opportunity right now and to talk about advantages. So in these simple examples, you can go and make those spirals directly in the FX map node, but separating it, also separating the drawing and the data, it's maybe a crucial thing to do because you actually have access to the data right now, and you can use every node in Substance Designer in order to change this data however you want. So what, for example, if I will place a transform node here and place the transform node here as a result, and then get into the transform node, change the mipmap mode to manual, and starting to change the mipmap node is giving us like really interesting results. So yeah, that is cool actually. So this is the reason why separating the data from the node might be interesting, because between this node and this node you can plug a number of other nodes that will allow you to modify the data however you want. Okay, so I right now just want to shrink this spiral a tiny bit, and for this I will input a levels node in between these two here. So levels node, and I will decrease the luminosity or the brightness. So this is the second spiral and this is the level node, and if I decrease the luminosity you can see the spiral is decreasing. Plug this here and you can see we have two spirals together. And right now if you change this, those two spirals are changing in the same way. Good. The last thing that I want to do is use these lists of points to create lines between the corresponding points of the spiral. So we will create lines from this point to this point, and this point to this point, and this point to this point. Good. So we will start again with another FX map node from scratch. Make it black and white. Plug in the first list of position, the second list of positions, go inside. In this case we're going to use a square instead of a disk. Iterate node 256 times. Set this as an output or set this as a root. And in this case we're going to do things differently and a bit more efficiently. So in the quadrant node we are going to compute everything that we need into one single channel, and then output or declare some variables in this channel and then call those variables into the relevant subsequent channels. So we will compute a position, a length, and an angle for every line that is going to connect the 2 points of every of those 2 spirals. So going inside the luminosity, first of all we're going to compute the point where the center of those lines will be. We need to get in the dollar number, divide it by 256. Make a vector, bring in the first list, extract the only x and y components because this is what it's interesting for us. Duplicate this, read the second image. Now this is the first point in the spiral, in the first spiral, in the larger spiral. This is the first point in the second spiral, and in the one that was shrinked, and we want to compute the point that it's in the middle of these two, because that is going to be the center, or our line that is going to connect the 2 points. So we have the average float too. So this is going to compute the midpoint between the 2 points of the spiral. We're going to set this, and we're taking this result and we're saving it and giving it a name. So I'm going to name this position. Then we need to compute the distance between the pairs of points from our 2 spirals. So that's easy to do. We have the points here in this and this. We need to compute the distance. Set this as another variable, which we're going to name distance or length. Length, I think it's more appropriate. And then the last thing that we want to compute is the rotation or the angle of the line. I mean, and in order to do that, we need to subtract the points in the first spiral from the points in the second spiral, and then take the arctangent 2 of that, and the arctangent 2 outputs value from minus pi to pi, and we need to bring this into the range 0 to 1. So dividing by pi will move us to minus 1 to 1, and then we have another node which takes minus 1 to 1 and turns it into 0 to 1. So this is our rotation or angle. We're going to set this as angle. Great. And in order to output these things, or to make them available, we need to chain them somehow, and for this we're going to use the sequence node. And the sequence node is kind of like the lines of code. So this is the first line of code, and then if you put the sequence node, this is the second line of code, and if you put the sequence node, this is the third line of code. And right now we computed everything that we wanted, but the last thing that we need to output is the luminosity, because we are in the luminosity channel, and another sequence node is needed here, and then float. This is the value for the luminosity 1, which is white. Okay, good. So we computed everything. Now we need to call each of these variables into the relevant channels. We computed them, we need to access them right now. So going into the quadrant node under pattern offset, let me decrease the scales of the patterns in order to see how things are changing. So in the pattern offset, we're going to get a float 2, and we need to call position here and set this as an output. And you can see everything is around the spiral. Then we will go here into the pattern size empty function. Everything is white because all of our squares are large as the image itself and they are overlapping each other. We need to get in the length. The length is a float. So this is the length of the line, and we will also want to specify a width of a line. So the width is going to be something like 0.05, maybe 0.5, something like this. Okay, output this. So right now you can see the length of the line is computed and the width of the line can be controlled with this parameter. So 0.5. And then the last thing that we need to do is plug in the angle or the rotation. So under the rotation, go here, get plot, angle. Set this as an output. Great. So right now our line seems to be correctly aligned. And if we plug this here, you can see we have lines connecting all the points. Good. I want to show you a small trick. Maybe we want to offset the connections between the points, so we can make this line here connect not with from this point to this point, but we can make it to connect from this point to this point. So in order to do that, we just need to offset or shift from left to right this set of values. And we're going to use again the pixel processor node. We can use the transform node if you want, but I think using the pixel processor is better because repetition is good. Changing the size like so, getting inside, bringing in the values. Okay, and then what we want to do is move this from left to right. In order to do that, we need to add something to it, a vector float 2. And if we change the x component, you see that we're moving this from left to right. Okay, we are here. I want to see the results, plugging this in. It's giving us this result, which looks messy, but it is correct. So, or is it? I mean, if I plug this 0, something's changed. Oh yeah, so you need to do this 32 bits pixel, so that's why I'm getting an unexpected result. Okay, so right now everything is correct. Great. And the last thing that I want to do is, for example, I don't like those lines that are very long. Is there a way to delete them? And there is. We can go inside the FX map node, go into the luminosity, and instead of using a constant value for every line, we can change that. And the way we're going to do this is, if you remember, we already computed the length of the line, so we can see that those are longer than the others. And in order to delete them, so to speak, we will change their luminosity from white to black. And we're going to say that if the length is greater than some value, then make the luminosity 0, otherwise make it 1. So we need to do a comparison. Greater, if the length is greater than some value that we can modify, 0.3. And now we're going to use a conditional. So if this is true, then the luminosity is 0, otherwise the luminosity is 1. And instead of plugging a constant value, we're going to plug the result of this comparison. So you can see those lines disappeared. Good. And the last example is this one. And I'm going to, I mean not this one, but this one. And I'm going to show you how you can generate 16 points and then generate 16 rings of other points around them, and then you'll have the possibility to change the radius of each ring. Good. So
the trading account as portable has your favorite playlist. Download Awanda's award-winning mobile app and enjoy
Wow,
attractive spreads
I'm
on a secure
getting
platform.
commercials.
Open your account today.
Really annoying.
36%
And
of
I
users say they
apologize
lose money.
about this. Good. Okay, so I'm going to create a list of 16 random position. And to do that, I will use again the white noise. And this time I'm going to resize this to a resolution of 16 pixels by 1. So this is a tiny texture. I will duplicate this node and change the random seed, make a pixel processor node, plug the two values in, change the size to the same, 16 by 1, go inside, read the two list of random values. This is the first image, this is the second image, make a vector out of them, then output a float 4. Good. Another pixel processor node. This time we're going to make this 256 by 1. Bring the image in. Sample color. Okay, so this is a cool thing that it's happening, and I want you to be careful at one aspect. So we have an image which is 16 by 1, and then if we input this image into a larger texture, you can see that the first value that we have, this yellow vector here, we have it here, but it's repeated 16 times. And the reason why this is working is because our sample color node, it's the filtering mode is on nearest, so I want this to happen, so be careful to choose nearest here. If it's bilinear, you can see there is a transition between them, but I want this to be nearest. Okay, and I want to take a node that reads these values and output this like so. So right now we're getting a list of 16 points. In fact, we have 256 points, and at every dot here you have like 16 points sitting on top of each other. But the results that I'm getting visually, it's what I want, so I'm not going to bother with this too much. Okay, and the next thing that I want to do is I want to create a ring of other points around every single of these points. So we need to create another list or another list of values. Okay, good. So another pixel processor, of course, change its size to 256 by 1, make it 32 bits, bring in the initial position. So we will need these positions here, and we're going to create points around these initial positions. So read in the initial position, so get float 2, then sample, and then only extract the x and y component. And to this we want to add something. So these are kind of the centers of our rings, and the centers of our rings are defined by these parts, and right now we need to add the all the other rings here, and we're going to add something to this node here. Okay, so let me do this, duplicate this node here. We're going to extract the x value like so. We're going to multiply this by 16 because we want in this list, we want to create a set of 16 sub lists of positions. So multiply this by 16. and then our gradient is going to be very, very bright, but we will take the fractional part of this, and you can see we have right now we will have 16 repeating gradients. And if we remember from our past example where we created a circle and then we changed the radius in order to create a spiral, we're going to do the same thing here using the Cartesian node. So these are the list of angles, and we're going to multiply this by 2 pi because this is what our Cartesian node wants. And then Cartesian node, and this is our list of angles. Okay, and then we will plug a constant value for the radius for now. So this is angle, this is length or radius, and we're going to output this. Great. So going back here, I will plug this in here to see what's happening, and we're only going to see one ring, like so. What is happening right now is that we're having 16 rings sitting on top of each other, and this is the radius of the ring. And if we add this, if you remember, this contains the center of the ring and this contains the ring itself. If we now add this together, so this vector with this vector, and make this as an output, now we're having all the 16 rings sitting at their appropriate position. I'm going to duplicate this node, draw the centers, and draw the rings. Going to decrease the size of the circles defining the rings, like so. And the last thing that I want to do is there a way to change the radius for each ring to have a random radius? So of course this is possible. We're going to make a list of random radius for each ring. So in order to do that, we have how many rings? 16 rings. So it means that we need 16 different values. We will duplicate the white noise, change its seed, plug this in here, and instead of having a constant radius, we will have a radius based on those values here. Okay, so not like this, and then just sample the image one that it's containing the radius. I will output this and let's see the result and then explain what is happening. So plugging this in looks like a total mess, and the reason for that is because some of those values here are quite high, and this means that the radius of our circles is again high, and the value of 1 means that the radius of our rings is like the entire image, and we don't want that. So then going back to see the result, we need to multiply this by a value in order to have a parameter that will allow us to further control the radius of the rings. So multiply by 0 shrinks all the rings to 1 point, and then plugging this value allows us to further control the radius of everything. And then changing the seed here changes the radius. So yeah, these are the 4 exercises that I wanted to show. I will delete the previous examples and leave you with what we created from scratch. And these techniques of using pixel processor and fx map to generate data with pixel processor and then draw this data with fx map are really cool and interesting, and they will allow you a great deal of flexibility. So try to practice with this. For example, change this to color, try to go in those examples and change the luminosity, change the size, the width, the length of everything. Play with this until you get yourself familiarized with all these processes. And those techniques are very important building blocks that will allow you to create things for yourself depending on the situation that you have. So these kind of small exercises will allow you to will give you the basis of knowledge that you need in order to solve various real world problems that you'll encounter during your work or during your experiments and things like that. So yeah, thank you for watching this tutorial and see you next time.